Okay, we are ready to go with the second speaker of today. Arpith Kumar has come down from IISER Mohali to tell us about the complex Langevin approach I mentioned in passing in my lectures applied to the IKKT matrix model. So please take it away.
Okay, thank you, David, for the introduction. Good morning, everyone. So before I begin, I would like to thank the organizers for this wonderful opportunity. And so this work is based on a part of our current ongoing work with Dr. Anosh Joseph and Piyush Kumar at IISER Mohali. So the plan of this talk is to start with briefly introducing the IKKT matrix model and then moving on to the main motivation of our work, that is to probe spontaneous symmetry breaking and the associated sign problem. Then in the next part, we'll discuss a numerical method complex Langevin which can tackle sign problem and apply it to Euclidean IKKT matrix model. And we'll also understand why there is a need of introducing mass deformations to the Euclidean IKKT model before we can probe spontaneous symmetry breaking. So we'll discuss some preliminary results of our work, and we'll summarize with the future work. So IKKT matrix model. So in 1996, a zero-dimensional IKKT matrix model was introduced as a promising candidate for non-perturbative formulation of superstrings. So it's a zero-dimensional model and matrix model, and in the large N limit, it is the non-perturbative definition of 10-dimensional type 2B superstring theory. It was originally derived from the Green-Schwarz action of the type 2B superstring with Childs gauge. And it can also be derived from dynamical compactification of 10-dimensional n equal to 1 super Yang-Mills. For our interest, we'll focus on the Euclidean version of the IKKT matrix model, which can be obtained by Wick rotation from the Lorentzian version. So the partition function and the action is given by these equations, where the bosonic field matrices x mu transform as vectors, and the fermionic field matrices psi alpha, they transform as Majorana-Weil spinors. So these matrices are taken in Hermitian traceless basis. So the gamma matrices are constrained by under Weil constraint are 16 cross 16 matrices, and we haven't mentioned the charge conjugation since it's an identity operator in this particular constraint. So it was studied that the partition function of the Euclidean IKKT model is well defined and finite. So this model IKKT has in the Euclidean action is invariant under the following three symmetries. So first is the gauge symmetry, SUN gauge symmetry, which is inherited from directly inherited from the 10-dimensional n equal to 1 super Yang-Mills. The second is an extended n equal to 2 supersymmetry over a maximal n equal to 1 in 10 dimensions. So it includes the information about gravity. So this third symmetry is our main focus point of this work. So this SO10 symmetry, rotational symmetry, is broken into smaller subgroups, SOD, and this implies that the gravitational degrees of freedom can be interpreted from the matrix degrees of freedom, and this smaller subgroup SOD can be realized as the symmetric vacuum of the IKKT matrix model. So the cause behind the spontaneous symmetry breaking is associated with the fermionic contributions to the model. So after integrating out the fermions, what we have is the Pfaffian of a matrix, and that we'll see that how it plays a role in spontaneous symmetry breaking. So we have this fermion matrix after integrating out the fermions, and its properties are it's antisymmetric, and more importantly, it has a complex nature. So the Pfaffian has a complex phase associated with it, which fluctuates widely. And so if we take a phase sequenced method, if we ignore this phase, so the theory would not be exact and it would be missing some information. So, there were Monte Carlo and 1/d expansion studies of the bosonic part of the IKKT model, and spontaneous symmetry breaking was not detected. Later, there were phase sequenced IKKT model study using Monte Carlo, and again, there was no spontaneous symmetry breaking detected. So the reason they took phase sequenced is associated with the sign problem, as David discussed in his lectures. So the Boltzmann weight, because of the complex phase, can become negative or in general complex, and hence it cannot be interpreted as the probability weight. So this is the sign problem associated. So in conclusion, it is the complex phase of the model which is responsible, which should be responsible for this spontaneous symmetry breaking. And the idea is how to incorporate this, this complex phase in our study. And complex Langevin works perfectly for such scenarios. So as we were discussing, if the actions, suppose we have a complex partition function with a complex action, so it cannot be interpreted as a probability weight. And but complex Langevin, so Monte Carlo cannot be applied in this case, but complex Langevin can tackle sign problem for such complex actions. So complex Langevin is based on stochastic quantization. That is, the expectation values of the observables can be obtained as equilibrium values of a stochastic process associated with some probability. So to understand this better, let us consider a zero-dimensional theory with a complex action S, and the evolution of the fields phi is governed by this Langevin equation, where mu is the drift, which is the negative of the gradient of the action, and it has a Gaussian noise, a real Gaussian noise associated with it. So the figure on the right depicts this Langevin evolution equation. So it's a complex field configuration plane, and the arrows are denoting the direction of the drift, and there are some stable and unstable fixed points coming from the action. So we consider some initial configuration at start of the Langevin time, and the field configurations evolve, and with the help of the drift, these arrows, they migrate towards the vicinity of the stable fixed point, and instead of directly collapsing into this fixed point, they form a cloud around it because of the noise, the Gaussian noise. And in our simulation part, we remove this this migration towards the fixed point. This is known as thermalization. So the expectation values of the observables are then computed using stochastic quantization as the equilibrium values of associated equilibrium values of this probability distribution around the cloud. So we have the observables, we can compute the observable, but the question arises, what happens at the large Langevin time? So for large Langevin time, it is expected that this probability distribution has to mimic the original Boltzmann weight of the theory. So for real actions, this is indeed true. There is a proof of convergence, but for complex actions, there is no mathematical proof that exists. So to check the reliability of our observables that we have computed, we need to have some correctness criteria associated. So in the current literature, there are two such correctness criteria. So first is the Langevin operator acting on the observable, the expectation value should vanish. So the Langevin operator comes from the Fokker-Planck equation, which depicts the evolution of the probability distribution which we were discussing. The second is oriented towards the drift of the drift term of the Langevin evolution. So it defines the magnitude of the drift, and and the criteria is that the probability of this drift should fall off exponentially or faster. So for reliable simulation results, these criteria should be satisfied. So now we can move on to some applications. So to test our model, we apply, to test our method, we apply it to the bosonic IKKT model. And the Langevin evolution of the bosonic fields is given by this equation. The gradient is as follows. And we have a Hermitian Gaussian noise, which obeys this particular distribution. So to probe spontaneous symmetry breaking, we consider the extent of space as an order parameter, and which is defined as follows. And on the right, we have the expectation value of this extent for different n cross n matrices. So what we observe is that in the large n limit, the configurations are going to the analytical values. So so the large n limit so the simulations are correct. So they are converging towards the 1/d expansion analytical value, which is 0.25, around 0.25. But what we are focusing on here is that even for finite n, these extents are actually clubbed together. So there is no explicit symmetry breaking in these even due to the finite n. So there are no finite n effects which break the SO10 rotation, the SO10 symmetry. So in the large n limit, there is no spontaneous symmetry breaking, and even at finite n, the SO10 is intact. Then we'll move on to apply complex Langevin to the IKKT model. So the Langevin evolution is similar to what we had for the bosonic model, but there is an extra fermionic part. The gradient has this fermion matrix and its inverse, and we have the similar Hermitian Gaussian noise. And so when we try to apply complex Langevin to IKKT matrix model, we encounter two problems which violate the correctness criteria of the method. So namely excursion and singular drift problem. So we'll discuss these problems and resolve them one by one. So let's discuss these problems one by one. So first is the excursion problem. So in the Langevin evolution, these bosonic matrices may wander from the SU engaged group to an enhanced SLNC group. And if they venture too far away from this Hermitian group, so that results in excursion problem, and the simulation results are unreliable in that case because they violate the correctness criteria. So a simple and efficient solution to this problem is gauge cooling. And so we define a norm which checks the hermiticity of these matrices. And since these matrices are invariant under the following enhanced group transformation, and the hermiticity norm which we had defined is itself not invariant under the symmetry, we can repeat these transformation repeatedly to minimize the hermiticity norm, and we do so at each Langevin step. And after applying, so this is the hermiticity norm versus the Langevin time. So it's the Langevin time history, and we apply it for right now for finite n values, and for some parameter values, we find that the hermiticity after applying gauge cooling is under control. So gauge cooling does resolve the excursion problem. So the second is a more difficult problem, which is singular drift problem. And as the name suggests, it is related to the divergences in the drift, singularities in the drift. And so when the fermion operator has near zero eigenvalues, since it occurs when the fermion operator has near zero eigenvalues, and since the drift term has and includes an inverse of the fermion operator, the drift diverges for these near zero eigenvalues. And again, this violates the correctness criteria of complex Langevin, and the simulation results are unreliable in that case. So in a prominent study, it was proposed that mass deformations need to be introduced to counter the singular drift problem. And so the following mass deformations can shift the eigenvalues. So this form can shift the eigenvalues of the fermion matrices away from the zero values. And this, but the question arises, when we introduce these mass deformations in our model, what kind of symmetries are they breaking? So they explicitly break the SO10 rotational symmetry and even supersymmetry. So to recover the original model, we would need to take the limit of this deformed action going to zero. So in a recent study, the following deformation terms were taken, and so they do indeed shift the eigenvalues distribution away from the zero modes and resolve the singular drift problem. Also, they break the SO10 rotational symmetry explicitly, as well as the supersymmetry in the model. So to probe spontaneous symmetry breaking in the IKKT model, there is a need of taking, since there are two deformation parameters, so there is a need of taking three-way extrapolation. So the aim is that the SO10 symmetry, rotational symmetry will be broken to further to smaller subgroups, and which can be realized as SOD symmetric vacua. So they conclude that for the deformation parameter 3, mass deformation parameter for the fermion part 3, there is spontaneous symmetry breaking from SO10 to SO7, and as we go lower and lower, this group further divides to SO3, and there is no further division after that. So in a way, so they conclude that SO3 is the symmetric vacua of the IKKT matrix model, and this result is inconsistent with the Gaussian expansion study in 2011. So in our work, we introduced supersymmetry preserving mass deformations to the IKKT model. So it has a bosonic mass matrix, a fermion mass matrix, and also a Myers term is included. So under these following transformations, supersymmetry is preserved provided that the following constraint is respected. And a solution to this constraint is the following: are these deformation parameters. And so we obtain the following mass deformed action, and we need to check whether this mass deformed action indeed resolves the singular drift problem or not by shifting the eigenvalues of the fermion matrix. And so these are the eigenvalue scatter plots. So for delta equal to 0 represents the original IKKT model, and it does have singular drift problem since the eigenvalues are clubbed around. There are near 0 eigenvalues, and as we increase the so this delta is the deformation parameter in our supersymmetric preserving mass deformations. So as we increase the delta, these eigenvalues shift further and further away from the zero modes, and which indicates that these deformations does indeed evade the singular drift problem. So now that we have successfully countered the excursion problem, the problems and the singular drift problem associated with the complex Langevin method, we can study the IKKT matrix model. So to probe 5 minutes. So to probe spontaneous symmetry breaking, we would have to take a two-way extrapolation and going to large N limit and the deformation parameter going to 0. So so first we study the bosonic IKKT model with Myers term and the bosonic mass term. So we would like to check whether these terms which we have introduced in the bosonic part of the action, does they contribute to spontaneous symmetry breaking or not, and whether the original SO10 symmetry is restored in the delta going to 0 limit. And we have the same extent as the order parameter. We take a normalized extent in this case, and we find that for delta going to 0, after delta equal to 5 or 6 for n equal to 6, the SO10 symmetry is being restored, and in the delta going to 0, it's there is no spontaneous symmetry breaking. So these bosonic mass terms, these bosonic deformation terms, are not contributing to any to spontaneous symmetry breaking. So then we apply complex Langevin to the mass deformed IKKT model. So we take the normalized extent values on the y-axis, and on the x-axis we perform simulations for various finite n values. So for a particular deformation parameter, we observed that there is this explicit symmetry breaking SO7 cross SO3, and but there is a very soft dependence on n. So these normalized extent values, they don't change much with in the large take for at least for finite n values. So we are still working on the large n limit and how they would change with large n values. So this is the delta equal to 0 limit. So then for a finite n value, we take delta going to 0 limit, and for as discussed earlier, so for finite delta values, so we do have this explicit SO7 cross SO3 symmetry breaking. But as we take this delta going to 0, this symmetry breaking is retained. So this hints towards spontaneous symmetry breaking from SO10 to SO7 or even smaller, because these above these cluster of 7 extents, it is further breaking down into different values. But again, we would need to consider some large n extrapolations before commenting on the nature of the symmetric vacuum. So to summarize, complex Langevin is indeed a powerful tool to study complex actions. And what's more important is that it can detect spontaneous symmetry breaking in theories. And so we applied supersymmetric mass deformations to IKKT matrix model, and we confirmed that these deformations successfully evade the singular drift problem. And but large n extrapolations for these deformations are required to investigate the exact nature of the symmetric vacuum. So in that context, we are using noisy estimators to compute an approximate trace of the to approximate the contributions from the fermion gradient. So one more interesting thing could be to probe SOD symmetry, spontaneous symmetry breaking, using these supersymmetry preserving transformations for dimensionally reduced super Yang mills. So this work has been for supersymmetry breaking deformations. This work has already been done for. So we would like to check our results and check whether we will obtain the similar symmetric vacua. With this, thank you for listening.
Thanks, Arpith. Do we have questions on?
Well, the first one is a technical question about the Langevin method.
Yes.
How do you ensure gauge invariance in this case? I mean, the noise is not gauge invariant, but is there some way to guarantee that the answer is gauge invariant?
So, so gauge invariance. So I haven't studied in that context whether the noise would affect it or not. But in the enhanced gauge, there is this check which we are containing. So it's not exactly this, but one can check whether for a particular model where whether the theory is the simulations are gauge invariant or not. But for complex Langevin method in general, I don't know like whether it would be gauge invariant.
That's a technical question. Then go ahead to the plots. You had the bosonic one, and there seemed to be a first order phase transition.
Okay,
Keep on going there.
so
right for delta approximately
yes.
7, there was.
So so for very large delta values, so it appears that there is a phase transition. So this could be because of the finite n values. So the order of the value where it is occurring could be decided by the finite n values, and it is going from the IKKT bosonic model to probably for large delta values to Gaussian matrix model.
Right. So here's the question now. When you do this in the case with fermions,
yes,
what the fermions do is they kind of make the x get bigger.
yes.
So the same value of delta does very different things in the fermionic model and the bosonic model, because in the fermionic model, the x's are bigger. So the contribution of delta to any symmetry breaking is effectively larger because the configurations that contribute are bigger. So I think you need to go to much smaller delta in the supersymmetric case to make any claims. Yes.
So yes, that is right. And so we have been comparing this delta value with the mass deformations considered in this study. And so there is a factor which is different from what the mass deformations which we are considering. So we are actually going up to the similar scales, but again, as you mentioned, we would have to go to even smaller because that can be achieved with large n limit. So these the small delta values and the large large n limit are actually interrelated. So if we perform simulations for large n values, we can successfully evade singular drift problem and delta has to go low. Yes. So delta has to go lower and has to go higher. Yeah. So the Myers term produces a fuzzy sphere, a big one. Yes. Tries to do that. Yes. So when you make n bigger, that sphere gets bigger, and you need to suppress it more and more. So you need to take delta to 0 faster than n in some sense. Okay. So I'm gonna let someone else ask questions.
We are just about at the end of time, but if there is a quick final question.
This zero-dimensional matrix model have been obtained by type 2 matrix model.
Yes.
So it is compactified and with 10-dimensional manifold or 9-dimensional.
So it is compactified on 10 dimensions. So it's a zero-dimensional matrix model.
Okay.
All these dimensions have been compacted.
Is it like all spatial coordinates 9 tori or something other manifold?
So so this particular model we are studying right now is the Euclidean model.
Okay.
So they're all.
Okay, thanks.
And I think with that, we should thank Arpith again.